These are the tides and waves notes. Tides are the rise and the fall in the sea level. That's called a tide. And it's caused by one gigantic wave in the ocean. And it basically just goes back and forth. One low tide / high tide cycle takes about 12 hours and 25 minutes. So there's usually about 2 in every day. The tides are caused mainly by the gravitational pull of the moon. And again, this is something that's really important for you to remember because most people don't think about this. And it's really the moon and the gravitational pull between the moon and the earth that tugs on the water to create the tides. Some other things that influence the tides: the gravitational pull of the sun, that huge other celestial body out there, the earth and the sun and the moon all interact together in order to make the movement of the water. The distance the sun and the moon are from the earth at any given time, and then winds are also a very small factor that affect the tides. Tides tend to be high where the gravitational force between the earth and the moon are the strongest, along with the opposite side of the earth where the centrifugal force is strongest. So if you think about the earth, taking a look at the picture that's on your notes, you get a bulge of water on one side wherever the moon is, and then on the opposite side, where just making an extra bulge because of the way that the earth spins. And then if you have the sun on one side and the moon on the other side, each of those is pulling water towards itself. So that makes those bulges as well. The tidal range is the difference in the ocean level between high tide and low tide. That's again the tidal range. And then here you have some problems to do about high tide. The HT is the high tide, and the low tide, the LT, is 20. So if you have 30 and 20 and you subtract, you're going to get a tidal range of 10. So that's what you have to put in there. And then the high tide of 20, the low tide of 12, you just subtract, and you should get, hopefully you're saying 8. And then a high tide of 50, a low tide of 20, you're subtracting again, and hopefully you're saying that it's 30 feet. Don't forget about the units on there. Spring tides have the greatest range. High tides are higher and low tides are lower than normal. And these occur during the new and the full moons. Again, taking a look at the picture on your notes, that first one at the top is a spring tide because the sun, the earth, and the moon are in a straight line. So the way to think about it is spring tides are in straight lines. The sun, the earth, and the moon are all lined up, or you could have sun, moon, earth. Either way, if they're in a straight line, you're going to get a spring tide. These don't have anything to do with the season of spring. It's just called spring, so please don't think about it as having to do with the seasons. It doesn't. And then again, here's that picture. You've got the sun, the moon, and the earth, and then here's one of those bulges towards either one of those objects, if you want to think about it. And then the centrifugal force is going to make another bulge of water on the other side. Now imagine the moon is not here. You've got the sun, the earth, and the moon on this side. They're in a straight line. It's still a spring tide. Neap tides have the least amount of range, or the smallest range. High tides are lower and low tides are higher than normal. And these occur during the first and the third quarter moons. The earth, moon, and the sun form right angles. So think about it like this. A 90-degree angle is a neap tide. 90 starts with N, neap tide starts with N. So a 90-degree angle is a neap tide. And then if you take a look at the picture, you've got the sun and the earth and a moon up here in the third quarter phase, creating a little bit of a bulge. Not as big though. And then you've got the sun, the earth, and the moon creating a bulge on this side. And then again, take into account this 90-degree angle. 90 degrees, neap tide. The gravitational effect of the moon two big bulges of water form on the Earth, one directly under the moon and another on the exact opposite side. As the Earth spins, the bulge is going to follow the moon around. Essentially just like this. You have that bulge of water, and then there's the moon, and as the moon goes around, that bulge of water is going to travel around. Now, moving into waves. A wave is a rhythmic movement that carries energy through matter or space. In oceans, waves move through the seawater. And waves are caused mostly by wind, can be caused by earthquakes, if you want to think about a tsunami, and the gravitational pull of the moon and the sun. Most of the waves we see are at the beach, but these aren't necessarily called waves. They're called breakers when you see them doing this as they come up along the shore and they break and they fall over. As the wave travels in shallower water, it slows and eventually falls forward as a breaker. The most familiar waves are wind generated. Again, this is really important to think about the designation between tides and waves. Tides are going to be caused mostly by the pull of the moon, whereas waves are caused mostly by wind. Three things determine how large the waves become. The first one is wind speed. This is the speed the wind is blowing, usually measured in knots or nautical miles per hour, and 1 nautical mile is equal to 1.15 miles per hour. The duration refers to the time over which the wind blows. Winds in some areas may blow strong for long periods of time, which can produce large waves. And the third thing is called fetch, which refers to the distance over which the wind blows. If a wind blows over thousands of miles, the waves can get much larger than blowing across a small pond. So again, thinking about that as like the ocean. Oceans have lots of waves that can get very tall versus, of course, a pond. They're going to be pretty small. And then the main parts of the wave. This is going to be very important for you to know as well. The crest is the highest point of the wave. A trough is the lowest point of a wave. The wave height is the vertical distance, remember that's up and down, between the crest and the trough. And then the wavelength is the horizontal distance between two crests or two troughs. So we're talking side to side. And then here's the picture. You need to fill this in on your paper. You've got the wavelength at the top, from the top of this crest here across to the top of the next crest. And then here's the word crest. You fill that in right there on your paper. And then you have the wave height. You're going from a trough to the top of the crest, and that's the wave height. Although the box is on this side of the picture, this is where you need to write wave height, is right there. And then if the water were still, you'd have this line that goes across it. Wave movement. When a wave passes through the ocean, individual water molecules move up and down, but they do not move forward or backward. So you have to sort of think about it as a big thing of water, and it's the wave that moves through, not the water. The water stays still, but the wave is what comes through the water. So if you take a look at this page, you've got, here's the wave, and it shows you as the wave moves through what actually happens to the wave. But it's moving through the water. It isn't moving the water. So as the wave comes through, you can see how the wave catches on the bottom, and then as the wave continues to move along, it gets stuck on the bottom, and then the top is what continues to move on. And then once you get to a certain point where the wave can't hold itself up anymore, that's where the breakers are. And you can see that here along the top. It tells you about what happens. Wave movement. When a wave breaks against the shore, the crest outruns the trough and the crest collapses. And this is what's called a breaker, which we talked about earlier. In this case, water does move forward and backward when it actually crashes onto the shore. And then when waves are caused by wind, The wind's going to blow across the body of water, and friction causes the water to move along with the wind. If you've ever noticed on a windy day, if you're looking at a pond, you can see the little ripples form. The tallest wind-driven wave can only reach about 90 feet in height. But taking a look at some of these pictures, maybe you recognize them. And these are pictures taken from the Perfect Storm movie. This is the cover of the book for the Perfect Storm. And then thinking about tsunamis. Tsunamis were once called tidal waves, but they don't have anything to do with the tides. They're produced when an earthquake or other seismic disturbance occurs, and it shakes up the water, and then it causes one big wave to occur. They're very long, fast-moving waves, and they can have a wavelength of 150 miles. And they can travel at speeds over 450 miles per hour, which is as fast as these big planes go, or as fast as a jet goes. And then some of the dangers. In the open ocean, a tsunami may only have a wave height of a few feet. But then as the wave approaches the shallow water, it builds to heights that can reach greater than 100 feet. And then if you think about, or maybe you've gone to see the movie The Impossible, about the tsunami that happened in Southeast Asia in 2004, essentially there was an earthquake in the ocean, which made this little wave, and then as the wave travels away from where the earthquake actually occurred, that wave height is going to grow as it gets closer to the shore, just like what we talked about on that picture with the breakers. It shows the wave moving through the water until it gets caught on the bottom of the shore, and then it crashes over. And at this point, with a tsunami, it crashes over way far up into the land and then takes out homes and people, and all kinds of sort of disasters occur.